Thank you, Dana, and thank you everybody for listening. So as Dana mentioned, my background is actually combinatorics, and that's the part where I feel more comfortable, and yet random graphs has so many, as a field, it has so many applications, and complex networks is a prominent one, that I find myself collaborate with many other people here at Bar-Ilan and outside of Bar-Ilan, and it's a fascinating field. I hope that this introductory talk will serve you well. I'm not going to mention the Corona crisis at all, except for saying that if there is any typo or error, it's probably because of the Corona. We can't work this way, right? So let's start. What are we going to talk about? So it's going to be random graphs, just the basic stuff. I'll present the Erdős and Rényi model, and we'll focus on the evolution of sparse random graphs. That's maybe, okay, it's the earliest results and one of the most important results for sure. And then we'll discuss a bit what do we need from a model of the complex networks. Shlomo already mentioned a few characteristics that we want to find. And then, okay, here's a spoiler, we'll see that the Erdős and Rényi model is actually not a good model for that, and we'll discuss other models. Yet, the Erdős and Rényi model is going to be very useful for us. And whenever you see the outline, it means that it's a good time for questions, but you can also ask in the meantime if Dana allows. Okay, let's start. Why graphs? So, okay, you know that graphs are good models for networks, and networks are abundant, so we should study graphs. That's true, but I want to point on another, maybe even more basic point of view. Whenever you have a mathematical structure, be it a field, a group, a vector space, a topological space, you always talk about a set, and then the structure is a bunch of relations and functions satisfying some axioms. What is the simplest mathematical object that you can consider? So that's going to be a set. We always have a universe and an unary relation, a subset. Well, that's not interesting. How about a set and a binary relation? That is the most simple, interesting structure that we can think of, and that's a graph. And I think that this explains why it's so useful, because it is so basic. And why random? Well, that's because, I think mainly because we can't think of large concrete object, but also because of complex networks. And not the specific characteristics that were found in the 90s, but more simple characteristics. Complex networks are large, too large, sometimes too large to analyze precisely. You need a model. Usually, or maybe always, you cannot measure the network explicitly, even if it was small. And it changes over time. So it's better to work with a model, and the model is going to be random graphs. What's the general approach? We are going to have the set of vertices to be the set 1 to n. What do I mean by that? Two things. One, our graphs are always labeled. So we care if 1 is adjacent to 2, we have just that edge, or 1 is adjacent to 3, right? We care about labeled graphs. And n is going to be the number of vertices, I think, along the whole school. And n is going to go to infinity. We care about the asymptotics. So we're going to think of n as being large and yet finite. It's important. We are dealing with finite graphs. Okay. Since we're dealing with asymptotic behavior, I need to define what with high probability is. So let's say that you have a sequence of events, and I just want to make sure that you also see the mouse, right? This little hand.
Yes, we see them all.
Thanks. So we have a sequence of events, an, and in particular, we don't need to assume that they are all in the same probability space. We may have, and actually that's the situation, a sequence of probability spaces. And AI is an event in the ith probability space. And we say that an, the sequence, holds with high probability if the limit of the probability of an being true tends to 1 as n tends to infinity. Okay, so that's with high probability. The example to have in mind is that you pick a graph from this over the vertex set 1 to n, so that's your probability space using some probability function, and say that an is that graph being connected. Then you have a sequence of events. The events an is the set of connected graphs over all graphs with, say, that set of vertices. Okay, and I'm going to use the standard lambda notation. F is little o of g if ever f over g tends to 0, and f is big O of g if there is some constant such that fn is always smaller than c times g of n. Okay, how should you think about that? Little o means that f is asymptotically smaller than g. If f is big O of g, it means that f is asymptotically not larger than g. And that's very useful, and I'm sure that most of you know that. Okay, so let's talk about random graphs. If I'll tell you to choose a number between 1 to n, you will assume that I want you to choose a number with uniform probability. And I think that that's the way things started. We can go back to 1947, more than a decade before the seminal papers of Erdős and Rényi, and Erdős then published a lower bound for the diagonal Ramsey numbers. And the way he did that was using random graphs. I'll actually tell you more about the details. So he actually thought about picking a graph uniformly at random from all possible graphs with n vertices. And then he noticed, that's a key observation, even though it's very simple, that this is exactly like choosing each edge independently with probability half uniformly at random. Why? Well, because if you have a graph on n vertices, you have n chooses 2 possible edges, and the number of possible graphs is 2 to the n choose 2. Now pick your favorite graph on n vertices. Let's say it's g. What's the probability of seeing g? Well, you need, let's denote the number of edges in g by e of g. You need these e of g edges to be in the graph. Each one happens with probability half, and we assume independence. So we get half to e of g, and the rest of the edges shouldn't be there. So that's again probability 1/2, and that's the number of the rest of the edges. And everything cancels out nicely, and we get 1/2 to the number of graphs. So picking graph uniformly at random is like picking each edge uniformly at random independently of all other events. And once you see that, then actually it's very natural to do the next step and replace half by p, and that's what Erdős, this guy, and Rényi did. And we get the definition of the Erdős-Rényi model. Now, I must say that historically, Erdős and Rényi didn't work with that graph, and actually that model was suggested by Gilbert before. But we give the credit to Erdős and Rényi because of the work that they did, and the way we think about random graphs stems directly from their work. So I think the name Erdős-Rényi model, even though historically it's not accurate, actually that's the right way to call the model. So what is GNP? GNP is how we denote the Erdős-Rényi model. GNP is a probability space over all graphs vertex set 1 to n, where the probability of g is what we said before with p replacing half, meaning p to the number of edges, 1 minus p to the number of non-edges in the graph. And this is exactly like choosing each edge with probability p independently of all other choices, all other edges. And critically, unlike in the case of p being half, p may depend on n, right? So as n goes to infinity, p can change depending on n. Okay. And here is an example of the way we work in a random graph. This is a nice example, quite easy. Okay, for that I need the following definition. What is a clique in a graph? That's basically a set of vertices all adjacent to one another. So a k-clique in a graph is a set of k vertices spanning all possible edges. Like any two vertices in the clique are friends. We denote the size of the largest clique in G by omega of G. So here's some computation. Some of the slides may be overpopulated. Don't let that intimidate you. Everything is very simple. Okay. We want to say something about the k-cliques. So the way we do it, we take x as a random variable, counting the number of k-cliques in G and P. In this case, G and half. Right? So let's make things very clear. G and half is a probability space. The sample space is graphs. A random variable is a measurement over that graph. And given a probability space, it has a distribution. And all we want to do now is estimate the expectation of x. Okay, let's do that. So what's the expected number of k-cliques? I'm using linearity of expectation here. I need to choose k vertices out of n, and once I've chosen that k vertices, I need all edges, all k choose 2 edges to be there. So we get that expression. N choose k times half to the k choose 2. And then I'm using a very useful bound, n choose k. I can bound it from above by e, and e is the constant, 2.71. En over k to the k. We're actually going to see that bound a few more times. And here I just replace k choose 2 by its definition. And then we need to notice that if we choose n specifically to be square root 2 to the k, then the expectation, things cancel nicely in the expectation, and we get that the expectation is e squared 2 over k to the k. And for k growing to infinity, this term tends to 0. Right? It's easy to see. Okay, so the expected number of k-cliques tends to 0. And another tool that I'm going to use is Markov's inequality. For a non-negative random variable, the probabilities of x is larger than a is bounded by the expectation of x over a, assuming x has expectation. In our case, the probability of x being greater or equal to 1 is bounded from above by the expectation. And that tends to 0. It's equal of 1. This means that with high probability, there are no k-cliques in G and P where n is square root 2 to the k. Okay, that's nice. Notice that the same calculation precisely goes for independent sets. Why? So independent sets are sets of vertices without any edges. And since we're dealing with G and half, the probability of having an edge and not having an edge is the same. So if we let y count k independent sets, we'll get exactly the same computation. And the same corollary with high probability. Now we can, if I get 2 events, each of them having with high probability, then the union also happens with high probability. So with high probability, G and half does not contain neither a k-clique or a k independent set, where n is square root 2 to k. And that's actually the bound, that's it. That's the bound on Ramsey numbers that I mentioned here. What's the diagonal Ramsey numbers? that's the list n such that in every graph with n vertices, there is either a k-clique or a k-independent set. And what we've just seen is that if n is square root 2 to the k, we have graphs, actually most graphs don't have either a k-clique or k-independent set. Okay, so this example illustrates the way we work and think with random graphs. Notice that even though this proof is very simple, this way of thinking is so powerful that actually that's more or less, up to a small improvement by Joel Spencer, that's the best lower bound for the diagonal Ramsey numbers. And that's not because of the lack of attention. Ramsey numbers or Ramsey theory is a cornerstone of modern combinatorics. Diagonal Ramsey numbers is, I guess, the most important parameter in that theory. So this simple proof is still very powerful. Okay. This uniformly chosen random graph has very high degree. Let's see that. Choose a random vertex, then how many neighbors it has, what's the degree. So it has n-1 potential neighbors. Each one of them is a neighbor with probability p. All in all, we get a binomial distribution with parameters n-1 and p. If p is half, the expected number of neighbors is n-1 over 2. That's a very large number. In real life, the expected degree is constant. Why? So I think that it's actually quite easy to understand. Degree is a local characteristic of the network. It's about how many friends you have, how many other routers your router is connected to. And you're not planning to connect your router to more routers because someone else installed another router somewhere, right? So you don't expect the degree to depend on the size of the network. Okay, so we want to focus our attention to sparse random graphs. Sparse means expected degree, a constant expected degree, sorry. And we are going to take a dynamic view of the model. That's another lesson we get from Erdős and Rényi. A dynamic view can be one of two things. Either you think of it as you start with an empty graph, a large independent set, and you throw in edges one by one, or, and actually it's almost equivalent, you can think of it as you change p. So p starts low, and then you increase the probability of seeing edges. And even though each time you change p, you pick the whole graph from the beginning, still this point of view works. Why? Because we'll see that many important graph properties are either there or not there, with probability tending to 1. Okay. Another overpopulated slide. Please don't be intimidated. Everything is easy. Okay, let's start. I want to say that p is going to be around 1 over n, and we'll see what we get. So we start with taking p being actually asymptotically smaller than 1 over n. Think of k as a constant, and to the minus, okay, so k over k minus 1 is larger than 1. This is n minus something that is larger than 1, so it's asymptotically smaller than 1 over n. More than that, we divide p by another factor, 1 over omega. So along the talk, omega is going to be a function growing to infinity. Usually I want to think about it as growing slowly. If you take omega of n being log n, that will work. That's slow enough for everything that I'll mention in this talk. But generally you can think of it as growing to infinity slowly. Here in this case, we even don't care about the slowly. What I want to say that here p is little o of n to the minus k over k1, k minus 1. Now let's see how many trees with k vertices we expect to find in G and P with that P. So again, we count these trees with xk. Xk is our random variable, is counting these trees, and we want to estimate its expectation. As before, we need to choose k vertices. That's the number of spanning trees over k vertices. That's K's formula. Usually it is taught in first year discrete math. If you never seen it, it's a beautiful result. Here actually all we care about is that this is a constant. And once we've ran over the k subsets, the possible trees, we need to require that we actually have the k minus 1 edges of the tree. Each one happens with probability p, and we have full independence. Okay, and now let's play with it. And choose k, we bound it by en over k to the k, as before. You can try to prove that bound yourself, either using Stirling formula or directly, it's not hard. K to the k minus 2 remains as is, and I substitute p for what it is. And again, because of the way we chose the parameter, everything cancels. This k minus 1 is this k minus 1, this n to the k with this n to the k, and this k to the k with k to the k minus 2, and we are left with e to the k, a constant, k squared, a constant, omega to the k minus 1. And omega tends slowly to infinity, so the whole thing tends to 0. And again, by Markov, the probability of having even one such tree tends to 0. Corollary, with high probability, there are no trees on k vertices. So we're talking about a very sparse graph here. On the other hand, I'm not going to prove that. If p grows a bit faster, asymptotically faster, than n to the minus k over k minus 1, then with high probability, every tree on k vertices appears in the graph. Okay, so what we've got is a very interesting result, right? We have a function, n to the minus k over k minus 1. And if you are just a bit, still asymptotically, just a bit below it, there are no k trees of size k. And if you're just a bit above it, then suddenly they all appear. We call that p a threshold function. This is n to the minus k over k minus 1 is a threshold function for the appearance of trees with k vertices. And this is not a rare thing. Actually, any monotone graph property, monotone means that if G has the property and you add another edge, G still, you add another edge to G, G still has the property. That's monotone increasing, and if P is monotone decreasing, meaning it remains when we remove edges, it's still monotone. So for every monotone graph property, you have a threshold function. So it's not a rare phenomenon. Actually, that's the standard case. Okay, so this P is actually asymptotically smaller than what I promised you we'll concentrate in, which is 1 over n, but you can think of it as the graph starts empty, and then trees with just trees of size 1, just edges starting to appear, and later on paths of length 2, and then trees with 3 edges, trees with 4 edges, and so on. As P gets closer and closer to 1, we get larger and larger trees appearing. And when we get to C over n, so now this is n to the minus 1, we call that regime the subcritical phase. So the subcritical phase is where P is C over n and C is smaller than n. When we get there, then cycles appear. Okay, and I wrote here 3 lemmas, if you like. Let's go over them. The first one states that if P is C over n and C is smaller than 1, ignore the blue part for now. Then with high probability, every component in G and P contains at most one cycle. Actually, this is a similar computation to what we did before. Just estimate the expected number of components with 2 cycles. You'll get it tending to 0. Here is another one. This one also talk about the subcritical regime where C is smaller than 1, but also about C being larger than 1. Anyway, if P is C over N and C is not 1, then the total number of vertices in unicyclic components, that is, in components having 1 cycle, is at most omega for any function omega. Why? So that may be a bit confusing. If you calculate the expectation, you get that expression. So here, K is the size of the component, and a unicyclic component can have size less than 3, right? That's triangle, the smallest cycle. And the expression looks like K doesn't really matter here, and C e to the 1 minus C to the K. So if C is exactly 1, what you see is 1, this K becomes important and the expectation grows. But if C is not 1, then C times e to the 1 minus C is strictly less than 1, and you get a geometric expression, geometric series, which converges to a constant. So depending on C, you'll get a constant, and anyway, it will be smaller than anything tending to infinity. In particular, the probability that the number of number of vertices in unicyclic components will be more than omega, again by Markov, that's at most 1 over omega. 1 is, I should have written here constant, that constant, over omega, and this is literal of 1, tending to 0. So let's summarize. Unless C is 1, unicyclic components donate at most a constant number of vertices to the graph. And here's the third one. Again, ignore the blue for now. Here we are trying to estimate the size of largest trees. So we said that there are no components with 2 cycles, only small number of vertices in components with 1 cycles, so we are left with trees. If P is C over N, C is different than 1, you can think of it as smaller than 1 for now. Alpha is some constant dependent on C. Then with high probability, there are no isolated trees of size, so this is a constant, logarithmic log of N. And now I'm going to go back to all the blue stuff, and the blue stuff is details. But what I wanted to show you is how accurate can we be. Okay, look, let's start here. I can actually take P to be 1 over N minus something going to infinity as slow as you like over N to the 4/3. And here, okay, I need omega to be literal of log of N. That's the only place I think. And then I know the size of the maximal tree almost precisely. You don't have a tree of size 1 over alpha log N, and I know the constant, minus 5 over 2 alpha log N plus omega. You don't have that. And with high probability, you do have a tree where the size is the same minus omega. So just a bit smaller. We know the size of the maximal tree almost completely. Okay, and so that was the subcritical phase. Let's summarize all the black and blue together. Here it is. If C is smaller than 1, then and P is C over N, then in G and P, 3 things happen. No components with more than 1 cycle. The total size of component with 1 cycle is very small, smaller than anything going to infinity, basically constant. And all trees are of logarithmic size. And we cover, I think, what is considered the first statement in random graphs, historically the first, that if C is between 0 and 1, then the size of the largest component in GNP, or P is C over N, is logarithmic. is most logarithmic, actually it is logarithmic with high probability. That's the subcritical phase, where C is smaller than 1. All the connected components are small and are basically trees or sometimes unicyclic. Okay. What happens when C is larger than 1? And okay, so in that case, this expression C times e to the minus C plays an important role in the computations, and it looks like, look on the mouse for a second, it looks like that, meaning it's growing, it is unimodal. It's growing first and then achieving a maximum at 1 and then decreasing. So for any C where C is greater than 1, there is just one solution for x e to the minus x equals C e to the minus C, where x is between 0 and 1. Okay, so we have another constant between 0 and 1. So when C is greater than 1, we know that we have one giant component. The giant here means that the size of that component is going to be 1 minus a constant strictly smaller than 1, other terms tending to 0, times n. This is a linear size component. When C was smaller than 1, the sizes were logarithmic in n. Suddenly, we get a giant component of linear size. And it happened all of a sudden, right? C was 0.999, everything was logarithmic. C becomes 1.001, we get a giant component. That's the number of edges. Another constant, what I want to say here, we have lots of edges. This, I mean, it's much more than the number of vertices, right? The number of vertices is that, and here we have C times that. Okay, it's hard to see it this way. What I want to say is the giant component is not simple. It's not a tree. It has many cycles in it. It has some complex structure. And the rest of the vertices, that actually you can learn from the properties of the subcritical phase that we've talked about. The rest of the vertices are in components of size at most logarithmic, that are either trees or unicyclic. Okay, and this result is also from the same paper of Erdős and Rényi. And today we know more, actually much, much more. And I want just to quickly describe it. So I'm gonna share my screen. Can you see me now? Or do you still see the board?
We can see you.
Okay, and so here's the thing. This is another way of getting the giant. So you can start with a graph of minimal degree 3, and we actually know quite well what happens with the degrees. Okay, so the degrees are going to be at least 3, but quite small, at least at the beginning, where C is just a bit larger than 1. But anyway, we know everything about these degrees. Okay, then we call that the kernel. Then we need to replace each edge with a path.
We still see the presentation.
You still see the presentation. Okay, so maybe I'll stop the share.
Okay, now it's good.
It's okay. They can choose to pin the video. Just
okay, so
video, and you will see it anyway.
Okay, great. And thanks. Then hopefully I'll be able to share the presentation again soon. Okay. Anyway, you get you replace each edge with a path, basically of logarithmic lengths. There is a distribution here, can be smaller, and that gives you 2 core. And after that, you need to grow Galton Watson trees. Doesn't really matter the details, but here we have some trees. of logarithmic size. Okay, so, and that goes for other values. Some of them may be small, some of them may be of logarithmic size. Okay, so back to the presentation. Let's hope it works. Okay, do you see the presentation now?
Yes.
Okay, great. So that's a structural result, and we know that quite precisely. Also, we know what happens during the phase transition when C equals 1. So everything is known quite well. What happens later when P is larger than 1? Well, as long as it is still smaller than log n over n, then G remains disconnected and the smaller components are still small trees. And basically we get the inverse process than the one that we had before. Trees are now starting to disappear. Larger trees disappear first. The giant swallows them. As P gets closer to log n over n, trees disappear more and more until we are left just with isolated vertices. And when the last isolated vertex disappears, the graph becomes connected. Okay. So that's the classic phase transition in the Erdős and Rényi model. It's quite astonishing that such a simple model can explain phase transition. Like you see, I think Shlomo mentioned water changing from liquid to gas, right? As you change the temperature from 99.9 to 100.1 degrees Celsius, something big happens. You get a complete change in the macro structure of the system. Okay, so the Erdős and Rényi gives us phase transition, and basically we get threshold functions, we get similar phenomenon for many graph properties. Full independency means that we can actually do things very accurately. I tried to exemplify that in the blue statements. We can do things very precisely, and it's a very good toy model. Whenever you want to check something on a random graph model, you should probably start with GMP. Why? Because it's the simplest and you have full independence. And graph theorists, of course, use it a lot. Many times for non-probabilistic results, right? Like Erdős result that we've mentioned at the beginning. There is no probability in Ramsey numbers. Still, random graphs are useful. Okay. Any questions about that part? Okay, great. Then I'll move on. If you have any questions, just ask. Okay, so Shlomo did much better work than what I'm going to do in describing what do we expect from a model of complex networks. Still, here are a few observations. What you see here is how many autonomous system a packet, an email packet actually, needs to travel before it reaches its destination. And you can see that this is very nicely concentrated, bounded from above by, I would say, 7, or if you like. I mean, there are larger cases, but they're extremely rare. And if that, I mean, an IP packet, it has a bound on the number of hops that it can take. If that thing wasn't bounded, if this number wasn't bounded, the internet would have failed. You may think that that's not a characteristic, not a global characteristic, but actually it is. What you see here is the same thing, but now it is divided into 3 different regions between Europe, I mean, in Europe, in USA, and both, or globally. And you see that you get the same distribution. Geography doesn't play a part, and size doesn't play a part. Okay, so distance tends to be small. Here is another example. These are, I think, quite famous Kevin Bacon numbers. How does it work? Kevin Bacon is an actor. We give him the Kevin Bacon number 0. If an actor played in a movie with Kevin Bacon, it has Kevin Bacon number 1. If an actor played in a movie with someone with Kevin Bacon number 1, it has Kevin Bacon number 2, unless he played with Kevin Bacon himself, and so on. And so you get a network of collaboration in movies, and quite astonishing. Okay. It's quite surprising to see that distances are again bounded. And you may think that it's because Kevin Bacon cooperated a lot, and it's true actually. Kevin Bacon, if you look on the expected Kevin Bacon number compared to another actor number, then the expectation of Kevin Bacon is quite small, but still it's going to be bounded for anyone. A better one could have been Sean Connery. Sean Connery gives you one of the smallest actor number that you can think of. Let's put them one besides the other. And the important thing is, even though the distributions are a bit different, so Sean Connery has more concentration on the left side, the important aspect is these numbers are bounded. Okay, so distances are bounded. And you may have heard about the 6 degrees of separation, famous experiments basically showing that you can get 2 random people in the world can get to one another. So in the going over the networks of only people that you know. So if you know someone, you are connected to him, and the distance in that network between 2 random people is bounded by 6. Another famous collaboration network is in science. Erdős numbers are, of course, bounded, but they tend to be larger than actual numbers. I think that's because even though the movie industry is segregated, the scientific industry is even more. So for someone from archaeology to get an Erdős number, it already needs to go through quite a lot. But still, the important thing is typical distances are small. And when we have that phenomenon, we call it a small world network. Another important feature is power law degree sequence. Let's denote the number of vertices of degree k by n sub k. And the observation is that n sub k behaves like some constant that may depend on the system size, or must depend on the system size, times k to the minus gamma. We call that a power law, because we get the power of, the number of vertices with degree k is the power of k. And you should notice that the size of the graph does not appear in the asymptotic behavior, so it's scale free. The asymptotic behavior k minus gamma is independent of n. If you want to look on a specific network, well, the natural thing to do is to take logarithm of both sides, and you get that log the number of vertices of degree k behaves like minus a constant time log the degree. Here is again 2 charts for autonomous systems at different dates. These are the dates. Yeah, I know it's quite old, from the late 90s. That's a highly cited paper that showed that, the existence of many power laws in the internet these days, by then. Okay, and how does it look like? So autonomous systems of degree 1, we have many, around 2,000. This is log scale. Autonomous system of degree 10, well, much less. But we still get 20, 30, I don't know, maybe there are two with 30-something neighbors. And this behavior is, the parallel behavior, even though it was, of course, known in science for a long time, things like zip flow were known. This is an unusual thing, right? We like to think, or we usually think about normal distributions. Right? Height of people is distributed more or less normally. And if you have the average guy, then let's say the average guy is 175 centimeters, then you don't get anyone being 3 meters, right? But here, the average is going to be, like, we have thousands of vertices to K1, so the average is going to be small. As the size of the network grows, you're going to see larger and larger outliers. If height was distributed according to parallel, then in your class there was one guy with height 5 meters. In your country there was one guy with height 100 meters, and the tallest one in the world, by now, I don't know, would have been a 1 kilometer height man. Oh, a 1 kilometer tall man. So this is, in a sense, unusual for us. Let's go back to GMP. How does the degree distribution in GMP look like? So if P is C over N, as we said before, the degree is distributed according to a binomial distribution with parameter N minus 1 and P. And since P is C over N, it behaves like a Poisson with parameters. Okay. A bit deeper result, not that hard to shows that actually the proportion of vertices of degree K is also close to the same distribution, meaning to the probability of a binomial random variable being equal to K. Basically, we have asymptotic independence between degrees. This means that Erdős and Rényi random graphs are not scale-free. A Poisson distribution or a normal distribution, another approximation of a binomial where P is in a different regime, are very concentrated. You're not going to see anyone that is farther than the expectation, more than a few standard deviations. And this is not a problem with specifically the Erdős and Rényi model. If you think about random graphs that graph theorists considered before complex network models were developed, we had quite a few, right? A uniform random graph, that's the model that Erdős and Rényi worked on, random regular graph, random geometric graphs, many other models. All of them are not scale-free. So we need to find something else. What about typical distance? Do we have a small wall phenomena? Well, typical distance says in the giant component of GMP, where P is C over N, then they are logarithmic. You can actually think of the structure that the structural result that I've shown, then many vertices are on the trees, on the Galton-Watson trees outside of the cycle. And if you just pick two of these, the distance is going to be already logarithmic. You may think that this is because, well, actually, the graph is not even connected, right? So in a sense, the distances are infinity. So even if you look after connectivity happens, as we said, at log n over n, look after connectivity, still the diameter, the shortest path between two vertices, behaves like log n over log n p, and p here is omega log n, so if omega is small enough, you still see distances that are logarithmic. All in all, what we know is that we need to find different models. And here we come to models of complex networks, and I'm going to tell you about 3 models of complex networks. And there are others, and I'm not going to give you all the details, but it will give you a nice picture of what we have and what can we do. The first one is called generalized random graph. The motivation is quite simple. You're saying, okay, the best feature of the Erdős and Rényi model was independence of vertices. I want to keep that, but independence, sorry, of edges, and I want to try to keep that, and yet I still need to have vertices of high degree. What am I going to do? So the trick is quite simple. Let's put weights on vertices. Wi is the weight of the ith vertex, and the probability of an edge will depend on the weights. So Ln here is the sum of all weights. This is basically a normalizing factor, and the probability of an edge between I and j is the weight of I times the weight of j divided by this normalization factor. And it's not hard to see that we retain some independence because these choices are independent of all other edges. Of course, there is some dependency going through the weights, but that's it. Okay, we denote it by generalized random graph and vertices, and that's the sequence of weights. And as we said, given vertex weights, the edges are independent. And a nice exercise is the following. If you take all the weights to be Cn over n minus c, then you get back Gn p, with p being c over n. So it is indeed a generalization of the Erdős and Rényi model. And sometimes it helps to choose the weights a triangle. In this case, I'll denote them by capital W. So Wi now is a random variable, and this random variable is going to be the weight of the ith vertex. So if you take the Wi's independently, identically distributed from a parallel distribution, then you get a scaled graph. Okay, I didn't plan to show you the proof. Actually, it's not that hard. You can find it in many sources. Oh, I forgot to say that many of the charts and many of the charts and figures that I showed are taken from a few sources. Maybe I'll send you the links at the end, but please don't use them without permission. Okay. So what's good about this model? It undergoes a phase transition, similarly to the Erdős and Rényi model. You need to require some nice behavior from, say, this distribution, or from the Wi, if you think of that as distribution. The average distance depends on the variance of W. So here it's not a distribution, but if you have a distribution, it will be the variance of distribution. But even if you don't, you can still compute the variance of these numbers. And if the variance is constant as a function, if it is bounded as a function of n, then the average distances are going to be logarithmic still. However, if the variance is unbounded, if it grows to infinity with n, then distances can get as low as log n. And this is very similar already. I mean, log n, I think, is considered small world. Okay. So that's the generalized random graphs. I think that it is less popular. Why? Basically because you need to condition on the W's. Otherwise, you don't get independence. The next one that I want to show you is the configuration model. The configuration model takes the straightforward way. You want to have some sequence of degrees. You want it, I don't know, to behave. You want a power law degree sequence. Tell me what are the degrees that you want to have. Let's denote them by T by D. That's the degree of vertex of the first vertex, the second vertex, and so on. And of course, we require that the sum of degrees will be twice the number of edges, as in every graph. And then we would like to pick a graph uniformly at random from all graphs with n vertices and that vector of degrees. Okay, so when we write that G is distributed like Gn vec D, this means that G is chosen uniformly from all graphs with degrees D. Unfortunately, there is no nice way of choosing such graphs, and that's where the configuration model comes into play. So, how are we going to do that? Maybe I'll start here and then I'll go back. Let's say that n is 8, and these are the degrees that we want to achieve, 4, 3, 4, 2, 1, 4, 4, 2. Then we take a set of points. The number of points is going to be the total number of degrees. 3 and 1 are the only odd numbers here, so this thing is even and hence legal. So I take a set of points. I think that I have 24 points here. This set is my W. And so I have 10 points, and I partition it into cells. The cell Wi is of size Di. So if I want to have degree 4 for vertex number 1, then W1 is going to be of size 4, and so on. And the next thing to do is to partition W into M pairs. And we're going to do that uniformly at random. It's going to look like that. So a pair here is denoted by an edge connecting them. Okay? And after you do that, you collapse Wi onto the vertex I, and you get edges. So let's denote the resulting multigraph. I denote it by gamma to stress that it's a multigraph. What we get after a collapse, the vertex set is going to be 1 to n, and if phi of x is the cell containing x, then we are going to get the edge phi x phi y whenever xy was a pair in this partition to n pairs. Okay, let's see it here. So we got this pairing, and then we collapse, and you see that, we get that. So say 1 is adjacent to 2, 3, 3 again, and 8. That comes from 1, so this point adjacent to this point. This is 1 to 2, 1 to 8, and twice 1 to 3. And for example, if you look on 3, you get these 2 connections to 1 and a loop. And indeed, we have a loop in 3. So, as I mentioned before, the configuration model may give us a multigraph. However, we are almost always interested in simple graphs, graphs without loops and without multiple edges. Counters are not connected to themselves, or we don't care about being connected to themselves at all, and they cannot connect twice to another outer. You cannot somehow be twice as friend with someone. Okay, so the model is nice if it produces simple graphs. So the first result that I want to show you is the following. Let's assume that the pairing is chosen uniformly at random. Then, so F, the pairing is chosen uniformly at random. Then, every simple graph having that sequence of degrees has the same probability. To see that, you just need to ask yourself, how many pairings are going to give me these graphs, this specific graph? And the answer is, well, once you see that y is adjacent to 2, twice to 3, and once to 8, then basically you get a permutation over the names of these edges, and that's it. So basically, the probability of seeing a graph G in a configuration model is a function of the degrees, and that's it. And the degrees are constant for all graphs, so we get uniform probability. And that's here's a theorem that I cannot prove now. That's the probability of getting a simple graph. Here, I wrote a relatively general statement. Let's assume, I'm sorry, maybe you're hearing my neighbor who's also teaching right now. If we bound the maximal degree by n to the alpha, where alpha is strictly smaller than 1/6, okay, so that's some kind of condition that we must have, then the important parameter is this lambda. Lambda behaves like sum of almost di squared over sum of di's. It looks like variance, right? So we've seen that the variance plays an important role even before. Once you set this lambda, then the probability of getting a simple graph behaves like e to the minus lambda squared minus lambda, plus lambda squared. Lambda squared minus lambda. Okay. And let's check a few cases. If all the degrees are the same, then we get here n times d squared minus t over n times t. We're going to get lambda being d minus 1. It's a constant, and that's going to be a constant. And the probability of getting a random regular graph from the configuration model, a simple random regular graph, a simple regular graph from the configuration model is constant, is strictly above 0. So we can use the configuration model if we want to choose random regular graphs. Okay, so that's what the theorem gives us. Depending on the degree sequence, you know if you can use the configuration model for that or not. Okay, and of course, once you get a simple graph, this statement means that you get it uniformly. Okay, is it useful for complex networks? Okay, so for that, I'm going to cite the following theorem. Given a graph, so usually in graph theory we call that the degree sequence. Here, the degree sequence is the sequence of n sub k, right? How many vertices of degree k you have. So I'm going to call that just the degrees. So dag of g plays the role of vector d, the degree of the first vertex, the degree of the second, and so on. Okay, so that's dag of g. Here's the theorem. Consider a graph with degree d. Then, the probability of getting that specific graph from the generalized random graph with a given weights, actually the weights don't play any role here, conditioned on the fact that the degrees that you got are actually the right degrees, does not depend on g. Meaning you get a uniform distribution once you condition over the degree sequence. Okay, so what does it mean? It means that generalized random graph conditioned on the degrees is exactly the same as the configuration model using the same degrees conditioned on being simple. Actually, the models are tightly related, and their usefulness for complex networks is very similar. In both cases, you can recover a power law degree distribution and a small wall phenomenon if you take the right degree. And I think that the configuration model is much more popular because even though you don't get independence of edges, as in the generalized random graph model, you can work with a very simple object, and that's the random pairing, this F. So F is chosen uniformly at random. That's for real. Unlike in the generalized random graph model that you had independency conditioned on the weights. So the configuration model is actually, I think, by far more popular, and it's a good model for complex networks. Okay. The last one that I want to talk about is preferential attachment. Preferential attachment is a dynamic model. What do I mean by that? Before, the models that we had before were able to choose a graph having some properties. A dynamic model tells us how this graph is actually built. Okay, so it's not only giving us an observation of the graph, but actually explains how it is being created. Okay, and preferential attachment is such a dynamic model. I want to say that I can turn GNP, the Erdős and Rényi model, into a dynamic model, but that's not a good model for complex networks. Okay, so I'm assuming I'm going to describe preferential attachment, and I'm going to assume that M, the number of out edges, is going to be strictly larger than 1. Usually people take M being at least 1, but the case of M being 1 is special, and I didn't want to look into that right now. You basically just get 3. Okay, so we're going to have a sequence of graphs. G1 is the first one, and there is no randomness in G1. It is simply the vertex number 1, just that, and M loops over it. And then at time t plus 1, sorry, assuming that I have, or I already have GT, and I want to get GT plus 1, I do the following. I add another vertex, the vertex t plus 1, and I connect it to M other vertices, that's the parameter M here, according to the following rule. The probability of yi being connected to a vertex W depends on the degree that W has on the graph at time t. And then I normalize. Okay, so the point is, if at time t W already had a large degree, then it has a larger probability of being a neighbor of t plus 1. And we get a rich gets richer phenomenon here. If somehow by luck a vertex started to have an unusual high degree, it's going to attract more and more vertices as neighbors, and its degree is going to get larger and larger. And you can estimate the degree sequence. This time it's the usual degree sequence, the number of vertices of degree k, and you see that at time t, this is the normalization factor, it behaves like k to the minus 3. Yay! We wanted that, right? We wanted to have a parallel. So we get a parallel. Actually, we get that specific parallel with gamma being 3. It's quite specific, but on the other hand, that's very impressive, right? And we see that phenomenon in many realizations where you have this rich gets richer phenomenon. We get a parallel distribution with gamma equals to 3. Say that people are entering into a city and they want to choose where to go now, so they are more likely to go to the market. Why? Because there are many people there, then to, I don't know, an abandoned field. And once they go to the market, they are going to meet all the people in the market. So if you have that kind of mechanisms, a rich gets richer, you're going to get a power law with a gamma in it. Okay. One of the criticism about preferential attachment is that it is very sensitive to the initial condition. If, for example, in some models, I add these edges one by one, and then after I added t plus 1 in the first edge, the second edge can actually create a loop or double edges, and sometimes you don't allow them. And sadly, sometimes this changes the asymptotic behavior. So here I gave a very simple and concrete example. The way I described it, we don't recover the small world phenomena. Distances are almost typical distance. The typical distance is almost log n. However, if I'll just change my definition by a bit, adding some kind of a parameter usually called delta here, but it's, I mean, the definition is not that nice. That's why it's not in presentation. Then I can easily get gamma being smaller than 3, and immediately, even if this delta, so here delta is 0, if delta is going to be minus epsilon, I'm going to get typical distance as log n. So basically, I'm going to recover small world. Here are some instances. M is 2. I started with a vertex with 2 loops, and you should think about it dynamically, right? So I'm adding the edges one by one, and the vertices here, so they are basically the first 10 here, okay? And then they are the first 10 here. And if you came early, then you have a much better chance of being one of the vertices with the larger details. Okay, so let's summarize this part and the talk. Random graphs. Random graphs are beautiful, useful for mathematicians, also outside of mathematics. An extremely powerful tool that I think revolutionized mathematics, yielding the probabilistic method. Yet, real-world networks have some characteristics that standard models of random graphs simply don't have. Specifically, being small-walled and having the power of the sequence. Within 3 different models, generalized random graphs that retain dependence but only given weight, the configuration models that let us work with uniform pairing, and I think among these two that are almost equivalent, this one is by far more popular, and preferential attachment, that is a dynamic model. It explains how we get a power law with gamma being 3. There are other options, other variations of these models, but I think that this gives you a nice contemporary picture of the state of the art. So thanks.